Hi, welcome everybody. Today we're going to talk about reaction mechanisms. And so really the goal of kinetics is to try and find the reaction mechanism. So you have this reaction and you're doing an experiment and you figure out the orders of the reactions, the reactants, and you then think to yourself, well, how are these atoms or these molecules coming together? How are they reacting? What are they doing with each other in terms of collisions to form these products? How many of them are colliding, and in how many steps is this occurring? And this is what the reaction mechanism is. It's a process. It looks at how the reaction occurs. It talks about the collisions, how many collisions are occurring at a specific point in time. And you could either have where you have, one reactant and it is, breaking down. That would be called unimolecular. You could have two substances. That would be called bimolecular. You could even have three, which is really rare, and that would be called termolecular. Now, we divide the mechanism, the steps in the reaction, up into something called elementary steps. These are the individual steps in the reaction. And again, you could have multiple where you have, like bi or termolecular down here, or you could have unimolecular where you have a single molecule involved. Now, normally you have a reaction that has multiple steps, and this is the sequence of events that occurs in the reaction. Now, what we look at is, and this is where things get interesting and relate to rate laws, is that when we have a individual step that we hypothesize is taking place, we can actually write a rate law for that step, and we can use the coefficients. That's something that you cannot do with an overall reaction. An overall reaction, you actually have to have it where you have the experimental data. But here, with the elementary steps, the ones that you are hypothesizing, those actually can occur using the coefficients as the orders of the reaction. And so the idea is that if you have one unimolecular reactant and it is reacting, that the coefficient would be 1 and the order would be 1, and you could write a rate law for that. Rate equals k times a to the first. If you had two reactants reacting in a single step, you could use their coefficients and you could use them as the orders, and you could write a rate law for that individual step. And if you had three reactants reacting together, you could write a rate law using their coefficients and write a rate law that would be acceptable for that step. You can only do this for the steps. You can't do this for the overall reaction. The overall reaction you need to do an experiment for. But these steps, they're coming from the experiment. So the idea is you experiment first, then you hypothesize what you think the rate law would look like, or the mechanism would look like based on the rate law. That's what we're trying to do here. So let's look at how this would work. Let's say that I do a rate law experiment and I come up with an overall rate law for something. And I say, okay, I did this experiment with NO2 and CO. And the rate law that I came up with was rate equals, and this is done by experiment, this is experimental, was rate equals K times NO2 times CO. Now this is my experimental rate law. Now what I can do with this is I can say, all right, let me come up with a mechanism. And the most important part with the mechanism, the steps, is something called the rate determining step. It's the slowest step. It is the step that will determine your overall rate law. Remember, you can write rate laws for individual steps. And the rate law for the slowest step represents and should match the experimental rate law. That is so important. So I look at my reaction over here. This was my experimental rate law. I then come up with a mechanism, and my mechanism is right here. I say it occurs in 2 steps. A slow step where 2 NOs come together, 2 NO2s come together, and form NO3 and NO. And another step where the NO3 from this first step reacts with CO and forms NO2 and CO2 in a fast step. So these 2 steps in a mechanism, look at what happens. In a mechanism, the steps need to add up to the overall reaction. So the NO2 will cross out with this NO2, the NO3 will cross out with this NO3, I'll be left with NO2, CO, NO, and CO2. That's my overall reaction. So the first thing is that the steps in a mechanism must equal the overall reaction. The second thing is I look at the slow step and I write a rate law. So I write a rate law for this and I say, okay, the rate law for the slow step is rate equals K1 because it's step 1. NO2, there's 2 of them, so it's NO2 squared. And then I compare it to my experimental rate law. And I see that's what I thought it should, that's what it experimentally is. This mechanism would be considered valid because it holds true to these 2 things. The slow steps rate law is equal to the overall rate law, the experimental rate law. The steps add up to the overall reaction. So again, the slow steps rate law is equal to the experimental rate law. And the steps in the overall mechanism add up to the overall reaction. That's what a mechanism is about, the steps in a reaction. Now this is easy because the slow step was first, but sometimes the problems are a little bit more difficult because the slow step is second. And that's what I'm going to show you right here. So here's, like a reaction between 2NO and Br2, it forms 2NO-Br. This is my experimental rate law. Now this could happen through, a one-step mechanism where all 3 react, but that's really rare. So we're going to have a mechanism that we come up with, and the mechanism that we come up with looks like this. This is my proposed mechanism. Now notice here the slow step is second. So I can write a rate law for that and see if it matches my experimental. So let's do it. So for step 2, rate equals K2, because it's the second step, times NOBR2 times NO. Well, this doesn't work. NOBR2 is called an intermediate. And we see that because NO2 is generated in the first reaction and used up in the second reaction. That makes it an intermediate. So it's a product in the first, and then it's used up in the second, called an intermediate. So now I need to do some mathematical kind of, mixing up here. And so what I do is I use the first step to get rid of NOBR2. I want to get rid of that intermediate. Now the first step is fast and it's reversible. Now because it's reversible, the rates become equal very quickly. And so I can write rate laws for the forward and the reverse. The rate law for the forward looks like this. Take a second to digest that. K1, NO, BR2. And the rate law for the reverse, I use -1 to show its reverse, times NO, BR2. And then I set them equal to each other because they become equal to each other. So here they are and they're equal to each other. And then all I do is I isolate the NO-BR2 term. So I just divide both sides by K-1 and I get this. Now, here's where things get fun. I take this NO-BR2 that's in my slow step here. So here's my NO-BR2 in my slow step. And I substitute in this entire expression. And there it is. Now it's substituted in. The K's got messed up here, but substituted in. And when I combine all the K's together, I get my overall rate law that matches. You might have to look at this and try it on your own, and we'll try problems tomorrow to go over this. But that's the idea. We substitute in the intermediate's value from the first step into where it is in the slow step, and we are able to get rid of the intermediate, and it works really nicely. This problem's harder and more difficult to do, but it comes up not that often, but it comes up every once in a while. So let's just summarize here. So a chemist, they're going to run an experiment and they're going to find the rate law. They're then going to use that rate law, they're going to propose a mechanism that's going to support that rate law. The mechanism has to have two properties. The slow step has to equal the experimental rate law, and the steps have to add up to the overall reaction. Termolecular mechanisms are not valid usually. If we have an intermediate, something that's created in one reaction used up in the next reaction, we have to get that out of the rate law expression by substituting in with the fast step components. Alright, we'll try some problems in class with this, and thanks for watching.